Okay. So if you look at, well, you can't really see it. If you, well, you can a little bit. So if you think about, you have a circle, actually you have a circle and you have a circle. This edge is the only thing that keeps it lined up going down the tape. And so something that has, I'm running it the narrow face against the tape. I really want to have a longer, and it's less likely to twist and get any kind of, and the less twist I have, the more probable that you can actually find the locations. Now, if you also look at the detail, look how much undercut that it's done and how much it's left. It's left a very, very small amount, so this becomes an extra weak board. So what we want to do is maybe change the depth of this punch so we have a wider, so we're saying, okay, this is a really weak board. It tends to break very often. So, I mean, these are the details that we want to try to begin to tell them. I mean, this is what I'm trying to get you to learn how to see on the line. Okay?
Okay.
You following the numbers? But you understand why I have to get so many numbers to start with from a fact standpoint? So I want to figure out why I'm so far behind. Why is this one so slow? Why is that one so slow? If the machine maker says I should be able to get close to this per hour, why? Oh, well, I'm using how much percent in this step? And so I can say, okay, if they said it's 85,000 and I've got 10% of my time in here, it's an 88 second, and this is about 18 seconds. So the real run time, the placement times, are only about 70 seconds. So I'm at over 20% just getting it in, calibration, and getting it out. So can I make that entry exit time, so 20%, 15%, or 10%? This is the thinking you're trying to do. But this becomes really complex and detailed, and this is why I said some of these, this is going to be a really complex, really detailed. So the other piece would be, we get the drawings out. We look at where the chips are placed. We look at the spacing between the nozzle pickups and try to find, are there any pairs of chips or three chips that actually are almost right over the same nozzle. If I can, I'll put down this one, and maybe move it a millimeter or a tenth of a millimeter. So how much is the least amount of movement I can do in the head? What's the sequence I can do? And if you look at the one that has, I don't remember which one, I was thinking it was this one, has, one of them has one connector, one of them has two connectors. But if you watch it with the connect, maybe it's these have a connector on it. Not only chips, but have a connector. Like, you know, the little push in.
Yes.
So on this one, it has a connector, and it goes over and it picks up two connectors, puts two in, goes back, picks up two connectors, puts two in. So why do you only pick up two? You've got 8 heads. You could pick up 8 nozzles. You could pick up all 6 at the same time. And just go bump, 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 bump. But the other piece is you do so you run the board, you do all the chips. And you come over here and wait. Then you put the board back to the beginning and pick up 2 and start over. And then you have to go back down again. So, you know, if you've gone up, why not start doing the chips that way? I mean, the connectors this way. So you start trying to eliminate the unnecessary action inside the machine.
Good. Wow, that's great.
And this is the programming that I want people to learn. And you think, oh, I can't learn the programming, but you can probably see, it's just an instruction set. So, okay, here's instruction. And go to this point, this point, this point, this point, okay? But then we'd have to get the drawings and say, okay, the pickup location is here, the head location is here. He moves X number of millimeters, I can move it 500 millimeters a second. So you're talking, we're now calculating in milliseconds. so thousandths of a second.
Yes.
Is we're trying to save a few thousandths of a second. When you start looking at the board, you're saying, gosh, to run this board, there's 50,000 moves that the machine has to make. I want you to realize the complexity that you're dealing with. And then we pick the easy things to improve. Then we can begin to optimize it better and better and better.
Yes.
Okay, so this is what I'm trying to chase you, to get you guys to think about.
Yes.
Okay.
Okay. Thank you.
It tends to break away. If I do it like this, I have a much shorter space and lower, and I have a much longer surface area to try to break away, so I have lower leverage, longer contact, less likely to try to peel and break away.
Yes.
So they've given you a way, and so we need to walk down and do.
Okay.
But you had some other things about how they handle it and some of the setup. But the other piece was the nozzle, the pick and place.
So what?
It's basically the nozzle picks it up, places it. So it's called a pick and place. It's X-Y axis. So it's pump, 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 turning them. So this is what they're talking about.
Yes.
That you need to rotate. What will it take to change?
No. Okay.
Yep.
Rotate.
What will it take? And see, they're basically giving away other people's intellectual property. That other companies doing this same chips on same type of a flexible substrate find that design more robust. It's more tolerant to rough handling.
Yeah. So so we can apply it.
Yep. So how much a change do you have to make? I mean, you're going to have to maybe change your circuit board. What's that going to take? How long is it going to take? How much stock do you have? I mean, this is just part of good design.
Yes.
I would have to agree with Samsung right away. I mean, and then we can draw off the technical reasons why. Like there's kind of a peel test as if you clamp the chip, how much force do you have to have before you can break it along that surface area? How much force does it take if you break it along this way? So I'm going to guess your force to pull it away will be much higher breaking it away from here. So it becomes more tolerant to abuse by the operators. I mean, you start to say, okay, this design is functional, but this design, it makes it harder. It's like the hokey-yokey kind of stuff. It makes it harder for the operator to destroy the part or to create an error.
Yeah.
But you're saying you don't really have that many errors. We can go downstairs and they have probably 50 or 100 rejects that they have piled off. Why aren't we working on those?
Yeah.
I mean, this is some of the stuff that the Kanban group should do. Is if I'm regularly piling up rejects, if I have enough rejects to pile up like that or do rework, I mean, you should be able to find good samples. You should be able to easily trace back to root cause. The hardest thing to do when you start trying to do root cause analysis is when you only have one failure a month or one failure every 3 months.
Yeah.
It's usually those are what's called a multi-dependent problem, which it requires this plus this plus this plus multiple things to. I'll show you set in the book. What do you use? Fiber?
Zalo. I said it for my manager.
Okay.
Yeah. Oh yes.
Okay.
He constantly asks me that's.
Yep. So but you've also had a number of things about a visual check, but it's so small, it's almost impossible to really see. And nobody wants to use magnifying glasses around here. I mean, so these feeders aren't maintained, or the nozzles. So